Determining electron configuration. For electron configuration, you can simply just follow along the periodic table. The first two columns are going to be the S block. We start in the first energy level, the first period. We go across, 1s2. We go to the next energy level, the next row, 2s2. We move across to the last 6 columns, the P section, 2p6. We go to the next row, 3s2, and we move across 3p6. The next row we have 4s2. The D section is a little bit weird. What makes it strange is we're only allowed to have 8 valence electrons, but the D section has 10 columns, which means we'd have 10 electrons there. So these 10 electrons are tucked into the previous energy level. So we have 3d10, followed by 4p6. Go to the next row, 5s2, 4d10, 5p6, and we go to the next row, 6s2. Now, if you look carefully at the numbers on your periodic table, you'll notice there are some discrepancies with which periodic table you're using, but the lanthanide series of metals goes to the bottom of the periodic table, basically so the periodic table isn't folding out onto 2 or 3 pages of paper. Now this section is going to have 14 columns, 14 new electrons. If we want to have these, we have to tuck them in very, very deep, otherwise they may come out, and that would disrupt the chemistry that we expect. So it tucks in 2 energy levels to the 4f14. We go back to the main periodic table, 5d10, 6p6, and we go to the next row, where we have 7s2, skip on down to the actinide series of elements, 5f14, followed by 6d10 in the main periodic table, and we finish up with 7p6. As you can see, I took up 2 lines doing the complete electron configuration, going all the way up to element 118. If we want to do shorthand, we always go for the preceding noble gas and count those as our core electrons, because noble gases always end in completing a shell or an energy level. We'll then follow it with all the additional electron configuration. With shorthand, you'll do this after each row. So we'll go helium, neon, argon, so on and so forth. Let's go ahead and try to apply the electron configuration to the following. Scandium. Scandium is element number 21. It occurs in the 3d1 slot. Since it's in the first half, that will be an up arrow, a positive spin electron. We go ahead and we fill in all the preceding orbitals with 2 electrons. Now as I fill, I'm trying to be careful to always fill up all my ups and then all my downs. This shows us 21 electrons, which is what we expected. It also shows us ending in the 3d position. To show it in longhand, we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Let's do it for germanium. Germanium occurs in the 4p section. It is 2 in. Up spin, filling 1 and 1 into the first 2 orbitals of 4p. Everything prior to that will be filled with 2 arrows, an upspin and a downspin electron. Again, I'm trying to be careful to fill all the upspins, followed by the downspins, within an orbital type before moving on to the next orbital type. To fill this out in electron configuration, longhand, we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. Let's try it with potassium. But the potassium isn't just regular potassium, it's going to have a -2 charge. Since it has a -2 charge, it's going to go out 2 additional spaces and going to fill in like scandium. Now we've already done scandium, and so it will fill in the exact same way. It'll finish in the 3d1. Everything prior to it will have 2 electrons into each orbital. This will end up giving us 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. We have our original 19 electrons, plus the 2 additional that were giving us the -2 charge. Let's go ahead and try with nickel with a +1 charge. Because the nickel has a +1 charge, instead of gaining an electron, we've actually lost an electron. So instead of having an electron configuration like nickel, it's going to have one like cobalt. Now when a transition metal loses an electron, to become positive, it first will lose them from the S section. The D section and the F section are going to be electrons that are tucked in. They are not valence electrons. So when we lose one from the outside, it can affect where we will fill the rest of the electrons. Now, nickel has only lost 1 electron, but in doing so, we don't get to leave 1 in the 4s. Remember, if we lose an electron, the Coulombic force will pull all of the electrons that remain inward. And so, that additional electron that is in the 4s will end up being part of the 3d. So, our longhand ends up being 1s2, 2s2, 2p6, 3s2, 3p6, no 4s, 3d9. Let's do manganese with a +1 charge. Manganese is perfectly in the middle of the 3d section, but when it loses an electron, it's going to fall back and be like chromium. Chromium and copper were listed as specific exceptions. Half-filled sublevels can actually cause a type of stability. And so if we have the 4s half-filled and the 3d half-filled, it's actually more stable than having a 4s completely filled and the 3d almost half-filled. Again, everything before will end up being completely filled with 2 arrows, one up, one down, to represent the 2 electrons in each of its orbitals. This gives us the longhand 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Copper on its own would be an exception. Copper with a -2 charge is going to gain 2 electrons. And so rather than being like copper, it's actually going to be like gallium. So we're going to have 31 electrons that we need to deal with. Gallium ends in the 4p1 section, so that's where we're going to put our arrow. Everything prior to it will be filled with 2 arrows, one up, one down, to represent the 2 electrons in each orbital. This will end up leaving us with a longhand of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Let's do one more with phosphorus. This phosphorus is going to have a -2 charge. Phosphorus has 15 electrons, but with a -2 charge, it's going to be like chlorine. Chlorine has 17 electrons. Chlorine ends in the 3p5. We'll go ahead and place our electrons in the 3p5. So upspin, 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 downspin, downspin, to give us our total of 5. Everything prior to it will have 2 electrons filling each of the orbitals. One up, one down, one positive, one negative. Upspin, downspin, clockwise, counterclockwise spin. Our longhand will appear to be 1s2, 2s2, 2p6, 3s2, 3p5.